second. So consider finite sets D and R of the same size. And let f be a function from D to R. The following statements are all logically equivalent. F is a bijection. What was the definition of bijection, by the way?
Being both an injection and surjection.
Being both an injection and a surjection. But with finite sets of the same size, what we're trying to say here is F is a bijection if and only if it's just an injection. You get surjection for free. Or F is a bijection if and only if it's a surjection. You get injection for free. And F is an injection if and only if it's a surjection. So one gives you both. I mean, that's not true for infinite sets. We'll give some examples of that later. But first, let's work on the proof to this statement. And what does it mean? And this is something very standard in math. What does it mean to prove the following statements are all logically equivalent? So before we do that, let's give the actual proof. What's the strategy? To say P, Q, and R are logically equivalent to each other, three propositions are all logically equivalent. It means P if and only if Q is true, Q if and only if R is true, R if and only if P is true. And remember, if and only if, well, I guess we should use P and Q. P if and only if Q is logically equivalent to P implies Q and Q implies P. Right? That's why it's called, instead of just logical equivalence, sometimes it's called double implication. So when you say three statements are logically equivalent, that means you actually have 6 implications. You have that P implies R, R implies P, P implies Q, Q implies P, Q implies R, R implies Q. But you don't have to prove all 6 of them. Okay? All you have to do is prove something of the following. So the following 6 implications are all true. Okay, however, a proof that all 6 implications hold need not include a proof of all 6. This is because implication, well, containment, is transitive. Okay, like we'll talk more later on about what transitivity really means. But transitive, in this sense, it means if A implies B and B implies C, then A implies C. So in this case, A implies B. If A implies B and B implies C, then A implies C. Okay? And you can see that that's the case, just by viewing implication as a containment relation. If A implies B, then instances in which A is true are contained within the set of instances where B is true. And if B implies C, then the set of instances in which B is true is contained within instances for C. Therefore, A is contained within C. All right, so this is true because implication is described, or can be described, as a containment relation and A subset B and B subset C certainly implies A is a subset of C. So if you want to prove all 6 of these implications, you only need some minimal number that, along with transitivity, gives you all 6. So, for example, if we prove that A implies, or I guess it's P implies Q implies R implies P, right? Then transitivity will give the remaining 3. Implications. Right? Given that P implies Q and Q implies R, this gives you that P implies R. Right? P implies Q and Q implies R, therefore P implies R. Similarly, Q implies R and R implies P gives you that Q implies P. And then R implies P and P implies Q gives you that R implies Q. Right? So if you just prove these 3, this cycle here, then the remaining 6 all come, or the remaining 3 of the 6 all come out by transitivity. What would be another one? Like, instead of proving all 6, what would be another set of less than 6 implications, which would give you the remaining, which would give you the remaining ones by transitivity? There's one more in this case. What else could you do? Instead of proving P implies Q, Q implies R, and R implies 3, instead of just proving...
You could go the other way around, Circle.
Yeah, sure. You can go the other way around. That's similar to what we just said, though. Or what else could you do? Something that's not a cycle like that. Let me get a little clearer here. If we prove...
Could you do P implies R, Q implies R, and R implies P and Q?
Well, when you use conjunction, R implies P and Q, that means R implies P and R implies Q. Something that's not a cycle. So here we're working with a cycle. So let one second. If we prove the 3 implications Then, sorry, I just wanted to write that out. P implies Q implies R implies P. Or you could prove the following four implications. P implies Q, and Q implies P, and then P implies R, and then R implies P. All right, then we get the remaining two implications by transitivity. All right, once you prove these four here, all right, R implies P and P implies Q gives you R implies Q. And then Q implies P and P implies R gives you Q implies R. So, that's another way to do it. And that's pretty much it with three statements. Yes. Anyone wants to say?
How useful would the second way be? Like, would there be cases where you would actually want to do that over the first way?
Oh, sure. It could be that if you tried to do this sort of cyclic arrangement, that one of them is just kind of hard or tricky, whereas these might be simpler.
Okay.
Yeah. I mean, typically the cyclic strategy is the one that's used, but it doesn't have to be, especially when you're dealing with more than three. Similarly, if four or more P, Q, R, S are all logically equivalent, then this means that the following it means that the following 12 implications are all true. So P, Q, R, S. So P implies Q, Q implies P, S implies Q, Q implies S, P implies S, S implies P, P implies R, R implies P, R implies S, S implies R, R to Q, and Q to R. So there's 12 of them there. However, a proof that all 12 hold, doesn't need to prove all 12. Proving these four implications, P implies Q, implies R, implies S, implies P, will give the remaining 8 by transitivity. Right? Or any other sort of what's called a strongly connected directed graph. Right? There are other strategies. Would be to prove something like P implies Q implies R implies P, and then Q implies S, S implies Q. All right, these five. Strategy would be to prove like this, which yields the remaining seven implications by transitivity. Basically, you have to have a directed graph in which you can make it from one proposition to the other in either direction. So you go from P to Q like this, and then Q to P like that. Here you go from P to S like this, and then from S to P like that. So there it is. The smallest number of implications is always just the cyclic arrangement, however. Okay, that's always the smallest. Okay, so let's prove the theorem now. Let's prove that proposition. All right, and we'll prove that 1 implies 2, 2 implies 3, and 3 implies 1. Okay? So the way you do that is, you say which one we're proving. First, we're going to prove 1 implies 2. How does one prove an implication? How does one prove an implication?
Assume the hypothesis is true and show that the conclusion must also be true.
Right. So that's the direct proof, which is usually the preferable one if you can do it. Right. So, but there's 2 other strategies. So 3 ways to prove A implies B is true. 1, direct proof. Assume A is true. Show B is true. Why does that work? Assume A is true. Show B, not is, but must be true as well.
Such a direct proof, it's kind of hard to explain how it works other than the fact that you're just showing that it works.
Think of the truth table for P implies, or for A implies B. Think of the truth table. Think of the truth table. All right. True, false, true, true. When is the only time an implication is false? When is the only time an implication is false?
The hypothesis is true and the conclusion is false.
When the hypothesis is true and the conclusion is false. So, assume the hypothesis is true, show that the conclusion must also be true. In other words, this doesn't happen. There's also the contrapositive proof. Assume B is false. Show that A must also be false. Again, the only time an implication is false is when the hypothesis is true and the conclusion is false. So assume the conclusion is false, and then show that the hypothesis must therefore be true, must be false also. In other words, this doesn't happen. And then contradiction. Yes. Proof by contradiction. Assume not A and B not is true. Find a contradiction. Assume the negation of an implication statement. Right? The only time the implication statement is when the hypothesis is false, is when the hypothesis is true and the conclusion is false. Okay, fine. Assume the hypothesis is true and the conclusion is false. Assume it's the case. Now, find some sort of logical inconsistency in that. All right? So, that is the three basic strategies for showing an implication is true. So here, we're trying to show F is a bijection, implies F is an injection. So assume the hypothesis is true, show that the conclusion is true. So assume that F is a bijection. So anytime you do a proof of an implication, you have to start out by setting up one of these. So your first sentence has to be a setup of one of these. Assume the hypothesis is true, or assume the conclusion is false, or assume B not is true. Or by way of contradiction, assume this is, A is true and B is false. The first sentence of an proof of an implication has to be one of those three things. If not, it's wrong. Unless it's 100% clear from some other context. Okay? If you don't have the correct starting point, well, the rest can't be true, period. I mean, it's like, if you're going on a trip and you got to go on I-70, and you get on I-70 and you go east instead of west, and you're trying to go to Indianapolis, well, you're not going to get to Indianapolis if you go the wrong way on I-70, right? So assume F is a bijection. What does that mean?
That is both an injection and surjection.
Right. So by definition, what?
Two is true.
Yeah. And that's it for that part. 2 implies 3. So, what is special about the domain and range of this function f?
They have equal number of elements.
Yeah, and it's finite, right? So assume that F is an injection. Okay, and let n equal the cardinality of A and the cardinality of B. So because F is an injection, or not A and B, I'm sorry, P, domain and range. Because F is an injection, the n elements of the domain are mapped to how many elements of the range? Every element of the domain gets mapped to one element of the range. But no two elements of the domain can map to the same elements in the range.
So it's still n?
Yeah. N elements in the range. Right? I mean, picture says 1,000 words here. Picture doesn't always say 1,000 words, but in this case it does. Every element in the domain maps to one element in the range, but no two elements in the domain map to the same element in the range. Right? Because F is an injection, the n elements of the domain are mapped to n elements in the range. But the range has how many elements?
N?
Yeah.
Equal.
Has n elements. Right? Therefore, the image of F is what? The whole range. Which means F is surjective. Right? What is image of F? It's all the things in the range that what?
Could you ask that again? I didn't quite catch it.
What's image of F? It's the set of all elements X in the range, right, such that X is equal to F of Y for some Y in the domain. Right? It's the set of all X in the range such that X is F of Y for some element of the domain. Or you can think of it this way. It's the set of all F of Y such that Y is an element of the domain. Right? So the image of F has to be the entirety of the range, which means what? What does that mean?
That it's surjective?
Yeah, F is surjective. Okay. Oops. Why is this not working? This is gonna crash. All right, so we've proven 1 implies 2. We've proven 2 implies 3. By the way, 1 implies 2 was a triviality, right? 2 implies 3 took a little more work.
Was 3 implies 1 should be a triviality too if you do it by contrapositive, right?
No, not contrapositive, because contrapositive would be that F is not a bijection. Oh, you're right. I'm sorry. You are correct. No, wait, hold on. It can't be. 3 implies 1. Surjection implies F is a bijection. Yeah, I mean, F is not a bijection means it's either not a surjection or not an injection.
Isn't it? Yeah. If
Right.
it's not bijection, it has to be one of the 2 properties.
Yeah, it's one property or the other doesn't hold, not one property and the other doesn't hold.
Okay.
Right, the negation of or is and. So 2 implies 3, 3 implies 1. All right, assume that F is a surjection. Again, let n be equal to the size of the domain and range. Okay? Because there are n elements in R, because F is surjective, the n elements of R must be reached by, at least n elements of the domain. However, there are only n elements of the domain. This is not really saying it right. Assume that, let's do this one by contradiction. How about that? Let's do this one by contradiction. Assume that F is a surjection and assume that F is, by way of contradiction, assume that F is a surjection, but F is not a bijection. By definition, what? By the definition of bijection, well, F is already a surjection. So by the definition of bijection,
It must not be injection.
F is not an injection. Therefore, what does it mean for F to not be an injection?
There's at least one element in the range that 2 elements in the domain go to.
Yeah, therefore there are 2 distinct x and y in the domain such that fx is equal to fy in the range. So the n elements in the domain map to at most what? At most, so I got n elements, but 2 of them go to the same guy in the range.
At most, all but one.
At most, n minus 1 elements in the range. So, the image of f is what? Is it all of R? Is the image of f all of R?
No.
It most certainly isn't. So f is what? Is not what?
Surjective.
Is not a surjection. A contradiction. Period. We'll have more of these later on in the semester. The following are all logically equivalent. But there's the first one. I'm not hearing a lot of discussion. I'm hearing the same couple of people talking all the time. Like I mentioned before, guys, the one tripping point in this class and in modern algebra, and probably in real numbers, real variables. I'm not sure what the course is called. In real variable sequence, is functions. I could, probably that's going to be the case. Okay, it needs a little extra time, a little extra thought. All right, final topic in this chapter, composition of functions. Given functions f from a to b and g from b to c, define the composition g following f, like that, from a to c by g of f of x is equal to g of f of x. All right, so the picture for this is as follows. Here's A, here's B, and here's C. Here's X, and there is f of x in B. And here is g of f of x, right? So you take x, you hit it with f, go here, and then you take f of x, and you hit it with g, and you go here. And then this is how you define g of f of x, or g following f of x. G following f of x. So things are written in this reverse notation. G following f of x. Please don't use this notation. This is people use this circle thing, to do function composition. It's totally like it will clutter up expressions and things like that. Just don't use it. It's bad. I don't know why. Textbooks insist on it. High school textbooks insist on it. So G following f of x, just write the functions next to each other. It's sort of a reverse multiplication. Okay, that's function composition. Let me write that down. So we say G f of x as G following, because it comes second. Right, because G is applied after f, so G follows f. So G following f means G comes after f, but we say G first, hence the word following. So, for example, now, of course, you did function composition back in your calculus days. Given f from the real numbers, and this is the generalization of that to the real numbers minus positive 3, sorry, defined by f of x equal to 3x plus 1 over x plus 2. So given f defined that way and G from R to R defined by f of x equal to x squared, we can define the following compositions. So G following f goes from where to where? So G comes second.
It goes from R minus -2 to
Right.
R minus 3?
Yeah, so it goes from R minus -2. Right, so you start with the domain here, going to this, and this, is contained within the real numbers, so you can think of it as just the real numbers, and then you go to R. I mean, you're not going to be surjective. You're going to, well, I think you will be, actually. No, this actually will be surjective. And will be defined by the way you did compositions before. G following f of x is equal to G of f of x. F of x is that, 3x plus 1 over x plus 2, the whole thing squared. All right, that's number one. You can also do f following G, right, which starts with the domain of G, right, which is the entirety of real numbers, goes to the entirety of real numbers. But then we're missing this -2 thing here. Right? We need to be missing the -2. But that's fine, because -2 is not part of the range of G. G, the range is actually the real numbers bigger than or equal to 0. So you're in no danger of hitting that -2. So that's fine. You take the whole domain of real numbers, you square them, right? And then you can apply f, because you'll never hit the -2, and then that takes you all the way to the real numbers minus 3 3. And this will be defined by g of f of x equal to, f of g of x, f following g of x, which is f of g of x, which is equal to, well, g of x is x squared, and then you apply that, this rational function, it's called a Moebius transformation actually, 3x squared plus 1 over x squared plus 2. All right, 3, you can also define GG from R to R, which is defined by what? GGX is equal to g of g of x, which is equal to x squared squared, which is x to the 4th. Normally, when you compose a function with itself, a function composed with itself is written as follows. So g following g is written g squared. G following g following g is written g to the 3rd. G following g, g to the 4th, so on and so forth. All right, so you can always compose a function with itself, and you just write this, exponential notation. By the way, function composition is not commutative. I mean, if both of them are defined. G following f and f following g are not the same. Oh, I'm sorry, it's 117. An example of that is what we've got, what we've been talking about up here. All right. Here's g following f, and there's f following g, and those are certainly not the same function. Okay, that's all for today. So we'll finish up chapter 4 next time, and then maybe do a little bit of an enrichment topic. Okay. All right. Have a good day, everybody.